Here is another application, the upside down Chu-Vandermonde identity. So what is it saying? This was again in lecture 16, I believe. No, I think it was lecture 15. So I'm just gonna copy paste it from the notes. This is what it's saying. Notice that n, x, and y are now non-negative integer. As I said, you cannot generalize it to real numbers. And now it's saying n plus 1 choose x plus y plus 1 is sum k equals 0 to n, k choose x, and minus k choose y. Again, I will state this proof as a double counting argument, and if you want, you can translate it into a bijective proof. So, double counting. So we count the x plus y choose 1 element subsets of brackets n plus 1, and we count them in two ways. First way, there are n plus 1 choose x plus y choose 1 of them by the combinatorial interpretation of BCs. That's the boring way that gives us the left-hand side. Now comes the conundrum. How do we get the right-hand side? By counting the subsets. So we have to split them apart according to some value, such that if this value is chosen to be k, the number of options is k choose x times n minus k choose y. It turns out that this way to construct them is the following. So we can construct such a subset by the following procedure. First, we choose the x plus 1's, or the x plus first, I guess, smallest element of S. I'm gonna call it S. So notice that this is well defined because x plus 1 is between 1 and x plus y plus 1. So let k be this element. And what will k be? Well, k is going to be between 1 and n because, between 1 and n plus 1, because of course it has to come from S and therefore also from n plus 1. Next, we choose the x elements of S that are smaller than k. So notice that because k is x plus first smallest element of our set, there have to be exactly x elements smaller than it and exactly y elements larger than it. This is how we can get an x plus y plus 1 element subset. Okay, so this means we choose x elements from the set 1 dot 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 k minus 1. Why 1 dot 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 k minus 1? Well, because they have to be smaller than k. So there are k minus 1 choose x choices for them. Because we're basically just choosing an x element subset of the set. So since we are choosing an x element subset of the set. Finally, we choose the y elements of S that are larger than k. This means we choose y elements from, so because they're larger than k, so the candidates start at k plus 1 and go all the way to n plus 1. So there are k, how many options are there? Let me say options, not choices. Well, we are choosing a y element subset of the set k plus 1 dot 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 n plus 1. As you can easily see, the set has n minus k plus 1 many elements. So on top you have n minus k plus 1. And at the bottom you have y, because you're choosing a y element subset. Altogether, we can perform this construction in how many ways? So in the first step, we choose a k. So we're summing the number of ways for each possible choice of k. On the second step, you have k minus 1 choose x options. And on the third, you have n minus k plus 1 choose y options. So in this many ways, or let me say the number of ways to perform this construction is this. But this is a little bit ugly because of the k minus 1. And if you look at this closely, n minus k plus 1 is also n minus k minus 1. So having k minus 1 in both places, we can substitute k for it. And this way, the summation bounds or both decrease by 1. So you get this. And this is exactly the right-hand side. So comparing the results of both ways, we find that this here is this here, which is precisely the upside down Chu-Vandermonde identity. So once again, we use double counting. We could just as well use a bijection and in fact scratch this double counting argument a little bit, and we will see the bijection hiding underneath. The bijection is on the one hand, you have the x plus 1 element subsets of n plus 1, whose x plus first smallest element is k. And on the right-hand side, you have a pair of a subset like this and a subset like this. And this bijection yields that the number of those subsets is exactly this product.